In the last lecture, we talked about how Earth's climate was in a glacial mode 20,000 years ago, and from this last glacial maximum, we moved to the present climate over a period of more than 20,000 years. Now, it is very important to understand how climate changed from the last glacial maximum to today, because there were several abrupt changes in Earth's climate during that period, and we need to understand what caused these changes in Earth's climate in this period. Now, all the changes in this period were natural climate change, nothing to do with human induced impact. So, it is very important to understand that in order to predict how will climate change in the future on account of human impact. Now, to study the climate of the Earth over the past 20,000 years, you need data. And the data that we have is primarily what is called proxy data. We did not have thermometers, and so we have to infer what the Earth's climate was in the past through indirect methods. Okay? Tree rings, ice cores, looking at the core at the bottom of the ocean, all these things are looked at to find out how the climate was in the past. This method is fairly complex, and of course there are some errors. So, in order to check how good these changes are, you need to complement the proxy data with climate models. Okay? We need to see whether climate models are able to reproduce the changes from the last ice age to today, okay? During which time there was hardly any human impact on climate. So, to cover this topic, I will be depending on many books. One of them is a recently published book called Global Warming Science by Eli Zimmerman from Harvard. It is a very good book. It is the first good quantitative introduction to climate change and global warming. There are many books you can see which have been published on climate change. Most of them are qualitative. They are meant for popular exposition and not meant for serious scientific discussion. So, this book was used for teaching students at Harvard. So, I think this is the ideal book for anybody who has serious interest in climate change issues. The other book which is very good is by Thomas Stocker from Switzerland. This is Introduction to Climate Modeling, because climate modeling is a very important part of understanding the past and the future climate. Okay? So, climate model has become very, very important now because of the availability of high speed computers. So, this is a good introduction to climate modeling with a lot of examples about numerical techniques and approximations. So, both these books I will be using extensively in my lectures. In addition, I will also be using a very important introductory book called Earth's Climate, Past and Future by William Rudiman. Okay? This book is somewhat more qualitative, but covers the entire spectrum of past climate and future climate, and has excellent graphics. So, I would strongly recommend that you have a look at the book. Now, in the dedication in this book, there is a very interesting comment which is relevant for our discussion. He says, this book is dedicated to my many colleagues who investigated science of climate change because they find it endlessly fascinating subject, and who in the recent years have in some cases done so under duress from those who refuse to accept what science is telling us. Now, this is a problem that is occurring mainly in United States, where there is a large group of climate change deniers who don't believe all the important discoveries that have been made in the last 60 years. And some of the scientists who were involved in these discoveries were actually attacked and were put under a lot of pressure by these deniers, and it took a lot of courage for many of them to continue to do the work. Now, this is an issue I will come to near the end of the course, because there are still lots of people who cannot believe that human being can alter Earth's climate. They think we are too small and we cannot do much to Earth's climate, but some of them may have changed their mind when the COVID epidemic hit the Earth 4 years ago, where a small virus which is not even 400 nanometers width, which we could not even see, had a huge impact on life. It completely stopped economic activity in most parts of the world. So that made many people realize that even small things can have profound impact on our life. So after this COVID epidemic, many people realize that carbon dioxide, whose concentration in the earth is just 400 parts per million, very small amount, can have an impact on Earth's climate. Okay? Before that, people thought all minor gases on Earth do not affect us. But today, but still there are lots of people who do not believe that human beings are changing Earth's climate. So some of the books I mentioned here were the first to explain the observation and show how models can reproduce these changes. And so these 3 books are essential reading for this course. Now, you must understand that when we want to look at Earth's climate from 20,000 years ago to today, there are lots of time scales. Okay? It is not time scales confined to human lifetime, which is approximately 80-90 years. The climate scales we are talking about are, if you talk about weather, it's mostly hours to weeks. Land surface responds from hours to months. Ocean surface goes from days to months to even years, because it has a deep layer of water. Vegetation can respond from hours to decades to centuries as the vegetation changes, as forest is killed or regrows. Sea ice can alter climate from weeks to years. Okay? In addition to these are called fast response. There are slow responses from mountain glaciers, which respond over a period of 100 years. Then your deep ocean, where a lot of heat is stored, that heat can come out after 100 to 1000 years. And ice sheets, which are large sheets of ice which are thick 1 to 2 kilometers, they can respond over a scale of 100 to 10,000 years. So when we study Earth's climate over the last 20,000 years, it's important to note that all these time scales play a role. Okay? And it is not sometimes easy to understand, because the scales are much larger than the scales that we human beings are used to. Now, here is a picture how Earth's climate changed over the last 60,000 years, okay, based on ice core data. Okay. This is the Greenland ice core, and based on the oxygen 18 isotope abundance in the ice as well as in the air. Okay. And when this delta O18, which we discussed a few lectures ago, is low, minus 36, this is high actually because less negative. This is a warm period of what we call Holocene, last 10,000, 12,000 years. But as you go in the past, you can see that delta O18 has gone down to as low as -42, which means a much colder climate. So what this picture shows is Earth's climate has fluctuated many times. Each of these events are numbered for convenience. So you see that there are many events of warming and cooling over the last 60,000 years, and the most recent one, which we'll discuss a lot in this lecture, occurred around 12,000 years ago, when the Earth rapidly warmed, and after that there was a period of fairly constant temperature, except a brief dip around 8,000 years ago. Okay? So this is a period which is well documented by data from proxies, and this is the period we want to understand. We want to understand this period because if you can explain all these ups and downs of the climate of Greenland using observation as well as models, then we have some confidence that our predictions of how climate will change in the future will be more reliable. So unless our climate models correctly predict these events, we cannot be confident about these climate models for the future. Okay? So that's the purpose of looking at this period. So the oscillations that are going on, there are many of them going on, are called Dansgaard-Oeschger events, and there are about 25 of them in this period. Some of the big ones are numbered. So during this period, the Earth's climate changed globally dramatically, and there were many changes in atmospheric and oceanic conditions, circulation, temperature, and so on. And the amplitude of the temperature change globally were in the range of 5 to 16 degrees. Okay? And there was brief warm period during the glacial time called interstadials, that is short warm period during a long cold period, and they lasted from a century to 1,000 years. Okay? So these are the periods we want to understand, because those oscillations went on for some time. Finally, Earth reached a stable climate around 10,000 years ago, and then remained very stable. So we need to understand why the Earth's climate changed so many times between 60,000 years ago and 20,000 years ago, and after that there was a warming, and when it reached around a period of 10,000 years before present, it remained very stable and constant. But of course, in the last 150 years it has gone up again. That's due to human induced change. So one needs to understand all these changes and see whether our ability to predict these changes is good, because if it is good, then we have some confidence that the climate of the future, which we will forecast based on these climate models, will be reliable. Now another close-up of the last 20,000 years, in which the present is right here, okay, warm period, and then the last cold period here called the Younger Dryas, which we will study in great detail in today's lecture, and various other ups and downs in Earth's climate. So there are two events which we will study in some detail. Coming from the last ice age, there was sudden warming around 15,000 years ago or 14,000 years ago, and it is called the Boeing-Ellerod event, in which Earth warmed quite suddenly, and then it plunged again into a cold period for about 1000 years before it came back again. So each time the earth became suddenly warm, a lot of ice melted in the polar regions, and these ice melt led to what is called meltwater pulse, that is a sudden rise in sea level. So sea level can be measured using proxy data very accurately. If you go to the beach and if you have good knowledge of geology, you can identify where the time when the sea level was higher than the present. Okay? So that people have done very carefully all over the world, and they saw two periods, one around 14,000 years ago and one around 11.3 years ago. In both occasions, due to sudden warming, the sea level rose rapidly. Okay? And this must be understood because the prediction of climate model is that due to human induced climate change, the sea level is again going to rise rapidly and may go up as high as 1 meter above the present by the end of this century. Okay? That is a large rise because that will essentially flood most coastal cities in the world. So you must know under what condition that will happen. So these two events we will look at closely, these two meltwater pulses, sea level rise induced by sudden warming. Okay. Now here is another close up comparing the proxy data obtained from Greenland and proxy data obtained from Antarctica. Two ice cores, one in Greenland, other in Antarctica. And I want you to notice there is a large difference between the blue and the red. Red shows drastic changes during Bowling Aneroid and Younger Dryas, while the blue does not show so much change. So what it means is, in Antarctica, the changes in climate are a little different from the Arctic, the northern hemisphere. So northern and southern hemisphere behave differently. Okay? As all of you know, the southern hemisphere Antarctica is a major continent, while northern hemisphere you have an Arctic Sea surrounded by land. These two are very different. Antarctica is very cold, it is at a higher altitude. So Antarctica behaves differently than the Arctic. For example, right now Arctic sea ice is melting rapidly due to global warming, but the Antarctic sea ice is not melting so rapidly because it is much colder. Okay? As all of you know, the temperature of ice has to go above 0 for it to melt. That has not happened so far in Antarctica, while in Arctic it is happening in the summer quite a lot. Okay? So I want you to notice that the changes in climate in the Arctic and the Antarctic are not same, they are very different, but the two are linked. The two are linked because ocean transports heat from the southern hemisphere to the northern hemisphere. Okay? So the southern and northern hemisphere polar regions are linked by ocean, one. Secondly, the atmosphere over Antarctica and atmosphere over Arctic are also linked because globally winds carry the air all around the world. That is why the amount of carbon dioxide in the Earth's atmosphere is almost same everywhere in Antarctica, Arctic, in India and America. Remember that at present most of the emission of carbon dioxide by the burning of fossil fuels is in major urban areas of the world which are located between 50 south and 50 north, but this CO2 ultimately reaches the Arctic and the Antarctic. Okay? So remember that Earth's atmosphere is one, it continuously circulates the gases in the atmosphere. So atmosphere provides a link between Arctic and Antarctic, and so does the ocean. So although Arctic and Antarctic behave somewhat differently, they are still coupled through the atmosphere and the ocean. Okay. Now, we are going to study in some detail the Younger Dryas event, at which time the earth cooled suddenly. Okay. And the name Younger Dryas comes from the emergence of flowers at that time, a flower which likes cold climate, and the flower is called Dryas, Dryas. Okay. And this event is called Younger Dryas because there was a slightly earlier period which is called Older Dryas. Okay. But this is more important period because it caused a glacial event in Europe, and this event was preceded by a warm event called Boiling Aneroid, which saw rapid retreat of large ice sheets in the northern hemisphere. So, these two paths of events, sudden warming and sudden cooling, has provided us very valuable data about how Earth's climate can change rapidly. Okay. We want to study this only because the climate is changing rapidly. Remember, in the period between 10,000 years ago and 1850, climate hardly changed. So, that period is not as interesting as this period from the point of view of climate modeling, because this period, Younger Dryas and Boiling Aneroid, are periods of large changes in climate in the Arctic and the Antarctic. It is a good period to check whether our climate models can simulate these changes. If they cannot simulate, then we cannot trust these models to predict the future. Now, here is another cartoon showing from 18,000 years ago, the last ice age. Earth was gradually warming, and there was sudden warming during the boiling oil, and then it changed. Okay, and so this rapid cooling is what we are going to look at. So, this is a recapitulation of what I said, that the onset of Younger Dryas, the cold period, took just 100 years. Okay, and that period went on for the cold period went on for 1,300 years. Okay, and North America cooled by around 3 degrees, and Greenland by 10 degrees, Europe by 4 degrees. But what is surprising that at the same time, southern hemisphere experienced warming. So, that was the thing which surprised people. Okay, and this period was characterized by abrupt change in the ocean circulation. In the ocean, the water deep in the ocean comes to the surface and goes north, and this circulation is called Atlantic Meridional Ocean Circulation, AMOC. Okay, and this has a huge influence on the climate of the Arctic and the Antarctic. Okay, let me again show you the cartoon which shows the cold period called the Pleistocene by geologists, and there was an event called Heinrich event, during which ice sheets collapsed and fell into the ocean, and after that came the Boiling Aneroid, sudden warming. Okay, and then the earth cooled again, and there was sudden cooling called Younger Dryas, and then it warmed again rapidly, and finally it reached the Holocene period when the climate was very, very stable. Okay, this is a period where agriculture flourished and Earth's population increased by more than 1,000 times. So, Boiling Aneroid is called an interstadial, that is a warm period during a glacial period, okay, which occurred between 14,690 before present and 12,890 before present. Thus, it went on for almost 2,000 years, this warm period. Okay. So, this was considered to be the end of the last glacial period, but this upward warming later caused Younger Dryas cooling. But during this period, there was a lot of melting of ice, and that ice fell into the ocean, and ocean sea level rise rapidly, called the meltwater pulse 1A. Okay. There are two pulses, 1A which occurred during boiling oil rod, and then the next one after Younger Dryas, again the earth warmed, meltwater pulse 1B. So, these two are important events because the sea level rose suddenly. Okay. Again, I want to remind you, starting from the past glacial age, Hendrix Stadial, where ice sheets were collapsing on the ocean and maintaining a cold climate. Suddenly it warmed, and that warm period lasted for about 2,000 years, and then suddenly it cooled, Younger Dryas, and later on it started warming again. The most interesting thing during this period is that we also have methane data. Okay. The methane came out during the warm period, and the methane increased suddenly. Okay. And that also was an important issue. Okay. This is a typical cartoon showing the collapse of the ice sheets. Now, when this happened, the large ocean circulation which transports heat from the tropics, where India is, all the way to the poles, this global circulation pattern was disrupted during these sudden changes. Okay. And this ocean circulation pattern has a volume flow of 20 million cubic meter per second. Okay. This is a large volume. Just to give you an idea, if you take all the rivers in the world, their volume around 1 million meter cube per second. So, this ocean circulation pattern, it transports 20 times the water that is transported by world's rivers. So, this is a huge system which has very large impact on Earth's climate. Okay. It has a surface warm water which is less salty because of rainfall, but once it drops into the deep ocean, it becomes cold and more salty, and this cold salty current flows deep in the ocean, and then it ultimately comes up in the Pacific and gains heat from the tropical region, and then goes as a warm ocean current at the surface, and then it drops around Greenland into the deep ocean. This circulation is driven by the variation density due to temperature and salinity. That is why I stress the word warm, less salty, and cold salty. The cold salty ocean has high density, that is why it sinks. Warm salty ocean is less dense, that is why it floats. So, this density gradient, although not very large, drives the whole circulation. Okay? And this circulation is very important for the Earth's climate because it transports heat from the tropics to the polar regions, and thereby keeps the temperature in the tropics somewhat manageable and makes sure that the polar regions are not that cold. So, this circulation pattern is very important to maintain the global mean temperature at 15 degrees centigrade for the last 10,000 years. So, this played a very important role. So, Heinrich event is a natural phenomena in which large icebergs break off from the what is called the Laurentide ice sheet in Canada, okay, and they come into North Atlantic. So, they were occurring quite frequently during the last 640,000 years. They are well documented, but they have not occurred much in the last 10,000 years. Okay. Now, these icebergs from the land, they also contain a lot of rocks that glaciers bring from land, and as they fall into the ocean, they create what is called ice rafted debris. That is, when these icebergs collapse and fall to the ocean, they bring along with them all these rocks from the land, and this debris falls into the ocean at the bottom and it deposits there. So, when we drill into the ocean floor and take out this sediment, we will see clear evidence of this debris. So, the ice rafted debris in the oceanic cores taken out of the ocean by ships, they tell us when the icebergs collapsed and when they fell into the ocean and how often this occurred. So, this is a very important data which you get from drilling deep into the ocean floor. Now, this is the Laurentide ice sheet. Okay. You can see that it is very large, covers most of the eastern Canada and part of the United States. There is another separate ice sheet called the Cordilleran ice sheet on the western side, that is not so large, so we will not talk much about it. This ice sheet, when it breaks, it drops huge ice and debris into the Atlantic Ocean. Okay? And we will be talking about that in the next few lectures. Now, here is a picture of the ice sheet coming and breaking off and carrying along with it a lot of debris of the land into this, okay, and falls into the floor of the ocean, where it forms sediment, and this is sediment that is taken out when you drill into the bottom of the ocean. Okay. On the right is the area where this deposit has occurred from the Laurentide ice sheet, and here is one example of the place where ships have drilled to look for this ice rafted debris. Okay. We will continue this discussion in the next lecture. Thank you.